Welcome to the talk for X-ray, approximating omnidirectional millimeter wave coverage using an array of phased arrays. Modern millimeter wave networking has been incorporating phased array antennas to compensate high attenuation loss. To overcome the field of view limitation, an array of phased array structure has been proposed and adopted by 802.11ay and upcoming 5G NR system. In an APA millimeter wave radio, multiple phase arrays are co-located, sharing the same RF chain but facing different angles to jointly cover 360 degrees in azimuth or elevation. Comparing to the single phase array millimeter wave radios, APA can potentially achieve omnidirectional Wi-Fi-like coverage by combining the coverages of each array. In addition, the combined coverage may provide more multipath diversity. That is, signals may traverse different paths through reflections, making it easier to save a link under blockage. However, there are fundamental challenges in designing APA millimeter wave systems. To address these challenges, we present a novel system called X-ray, which explores the challenges and opportunities from APA. The first challenge in APA is joint array beam selection. In an APA radio, the beam management problem is further compounded by the array selection. It will be impossible for the standard brute force beam searching method to select the best combination in real time. In X-ray, the client calls a lightweight AOD estimation algorithm and feeds back its estimation to the AP, which simply select optimal arrays and beams to activate from a pre-calculated lookup table. The second challenge is multi-array co-phasing. Due to the relative location and orientation differences among phased arrays, the emitted signals do not necessarily combine coherently at the receiver, causing RSS fluctuations up to 7 dB. This effect becomes more severe when UE is mobile. In X-ray, we propose a dynamic co-phasing design that proactively predicts and corrects the phase differences of arrays with low overhead. The third challenge in APA is blockage handling. It is well known that millimeter wave links are prone to obstacle blockages, such as human bodies and furnitures. In X-ray, we propose a link recovery mechanism that concurrently scans the beams on all arrays to quickly identify possible recovery paths. We implement X-ray based on an off-the-shelf 802.11ad AP. We reorganize the AP's physical layout and 3D print an antenna stand so that the field of views of different arrays partially overlap, and together they cover 360-degree azimuth. In addition, we hack the network interface card firmware and patch a piece of code to enable fine-grained per-beam RSS extraction, real-time codebook loading, and inter-array co-phasing, which are essential to X-ray's design. To verify whether X-ray effectively exploits the coverage advantages of APA, we conduct experiments with different number of arrays and by disabling or enabling its design components in a typical indoor scenario. We evaluate the case with 2, 4, and 8 arrays running X-ray, and a case with 4 arrays by disabling the array selection and co-phasing. We see although 8 array achieves similar coverage as 4 array, the areas with high bitrate links is much larger, thanks to arrays with partially overlapping FOVs providing co-phasing gains. Overall, with more arrays, X-ray eliminates all blind spots in the room, even for locations with thick walls. In summary, we have explored APA as a new paradigm to simultaneously improve the millimeter wave coverage and link quality. Our X-ray solution framework builds on the 802.11ad standard and runs directly on commodity devices. Our experiments have verified X-ray's advantages in terms of efficiency, coverage, and the ability to rapidly recover from link outage. For more details, please check our paper. Thanks for watching.